And if that is being detected, then it means you have no issue to deal with um, uh, the electrons. Only if after that you realize the thing is not balanced, that's where you have to pay attention to the electrons. Yeah. Please, can you guys see my screen?
Yes, sir.
Okay. So we're starting off with the unit 2 today, and I think the unit 2, what it talks about is the radioactive decay, radioactive equilibrium, alpha decay, beta decay, gamma decay, and radioactive nuclides and radiocarbon dating. So as usual, I'll be doing the radioactive decay, radioactive equilibrium, alpha decay, beta decay, and gamma decay with you. Then you read on the radioactive nuclides and radiocarbon dating. Okay. So starting off, we talk about radioactivity. And when we talk about radioactivity, I hope something comes in mind. So radioactivity simply means, as you already know, radioactivity. So it's a combination of two words, radiation and activity, right? And when you say radiation, is the emission of energy, right, in the form of light or something in the EM spectrum. And activity is any if you say activity, I don't know how to explain for you to understand this, but it's a kind of any action, or yeah, let me put it that way, any action or any phenomenon, right? So simply radioactivity talks about uh, releasing of energy by an atom, an activity, or an a phenomenon where a nucleus on an atom is said to releasing energy. And why do that happen? This happens when the atom is not stable. And I think we spoke about this last week, that when you find the, was it a binding energy or something? And if you get negative, it means the atom is not stable. Did we say that last week?
Yeah, I think in during one of the discussions, yeah, you mentioned it.
Oh, okay. So an atom is said not to be stable if, ideally, if the number of protons and the number of neutrons in the nucleus are the same, or if the nucleons are balanced. In that case, the atom is said to be stable. Okay. But in the case where the number of neutrons is more than the protons, the atom is said not to be stable. So in order for it to be stable, you have to release some of the neutrons in the atom. In the process of losing some of these electrons, they undergo radioactivity. Thus, they release a form of energy. And this energy is being released for it to be stable. So as it's being released, then the atom is becoming stable in that manner. So simply, radioactivity is the spontaneous transformation of atomic nucleus, leading to change in the composition or the internal energy of the nucleus. So as I said, it happens when the atom is not stable, and hence for it to be stable, it has to release some of its neutrons for it to be stable. And as we all know, in this world, everyone tries to be at an equilibrium state or a position where he's stable, because Obi Noah or Beko baby and people will be sacking him and he will be happy sitting over there, no. Or he will be in a situation where that situation is not comfortable, then he's being still there. No, no one will do that. So everyone is trying to be at a stable or equilibrium position. And it happens to these atoms as well. If the energy in it is more to the extent that it becomes unstable, it wants to be stable. And by being stable, that's where it's undergo radioactivity by releasing the excess energy in it for it to become stable. Okay. The decay of nucleus, hold on, is
Is that
yes.
why you say the release of the nucleus? I talk about nucleus because
Is that
if it's unstable, that means it has a lot of neutrons than the protons, right?
yes? In any
So for
other
it to
way, I
be
think I don't really remember, but then either one is more than one, it becomes unstable. For it to be stable, they have to be the same.
okay, so which one you release which one? You release the neutrons or you release the protons so that it
Is
will be
it?
stable. They said for it to go undergo radioactivity, then you have to release the nucleons, right?
Yes.
So yeah, the nucleons
Not
stand
not
for
not nucleons, not neutrons, but neutrons.
neutrons,
Yes.
the neutrons.
Yes.
Okay, okay.
Yeah. Because the neutron is more than the proton, and they have to be the same so that it becomes stable. So releasing the neutron is when it's undergo radioactivity.
Okay, thank you, sir.
All right. So the decay of nucleus of an atom can either be natural or artificial. Yes. We have some atoms that undergo natural decay or natural radioactivity, and we have some that undergo artificial. And some of the artificial one we all know is the uh, um, uranium 234. That's where we extract energy from the uranium in conducting or generating electricity. And some of the natural ones are the carbon 14 dating, which we use to track how old an artifact is. Okay. This decay occurs in nuclide in order that they may attain stability. As I said, if it wants to be stable, that's where they undergo radioactivity. And undergoing radioactivity, we are trying to say that it's being decaying. Okay, so uh, the decaying that is given to the atom is not uh, uh, a constant thing. It's not something that is going to be supplied to the atom constant, but rather it's just a one-time thing. It puts it to the state where it's very high. Okay, so when the atom releases that energy that was given to it to excite it, it comes back to its ground level. So it's the same process. Okay. The term natural radioactivity applies to the spontaneous transformation of one nuclear species into another with the emission of some particles, such as alpha, beta, antineutrinos, and neutrinos, and another with the emission of particles or electromagnetic radiation. So if these atoms are undergoing radioactivity, as I said, they release some form of energy. And some of the energy that they are being released is what we are seeing. Some of them is the alpha particles, the beta, neutrinos, and antineutrinos. And sometimes to reduce, they release gamma radiations or gamma rays. And gamma rays um, is a photon. I put it that way. It's a photon. Okay. So it's not always that the atom has to um, uh, I don't know how to put it. In other sense, sometimes the number of protons is being reduced or the number of neutrons is being reduced from the atom. But sometimes it's not the case. Sometimes it's just an energy that leaves the atom. And when the energy only leaves, that's where we are talking about the gamma rays. But in a case where maybe some of the protons in there are in excess or some of the neutrons are there are in excess, we want to take it off for it to be stable. That's where we have some of the emission particles as alpha, beta, or the neutrinos and antineutrinos. Okay. Natural radioactivity is displayed by the heavy nuclei at the end of the periodic table, that's beyond lead. There are also natural radioactive light nuclei, such as the potassium isotope and the carbon isotope, that's the carbon 14. And the carbon 14, I hope you know many uses of those kind of things. Now, the unit for radioactivity is disintegrations per time. Disintegration per time. And when we talk about the time, we all know time is how should I put it? When we talk about the time, we have SI units for time, which is in seconds, right? But in this case, when you are determining the radioactivity process, you can have it either in seconds or in minutes. And it's now split into further to either disintegration per second or disintegration per minute, based on the device that is used. Okay. But then disintegration per time is equivalent to becquerel. Disintegration per time is equivalent to becquerel. And this was the olden days unit for determining radioactivity. But as time goes on, this becquerel was converted to Curie, which was named after the French scientist lady Marie Curie. So even the becquerel in some books, they also stick to Curie based on the problem you are solving, because in some cases they can ask you to convert from either from disintegration per second to Curie or becquerel to Curie, and it's not something difficult. It's just a matter of knowing the conversion, and you'll be able to do that. Also, we have counting rates, and counting rate is a detection system are usually given in counts per second and count per minute. So as we said, we have disintegration per second or disintegration per minute. The same way we have count per minute or count per second. And this differ from disintegration per time by a factor. A factor. And the factor is what we know as the detector efficiency. So the detector efficiency, knowing the detection, the detector efficiency, you can convert also from disintegration per minute to count per minute, or disintegration per second to count per second. And that's what is the end. The detector efficiency is based on the device you are using. Note that it's always based on the device you are using. Okay. Now, an older unit of radioactivity that still finds some use is the Curie. And we say 1 Curie is equivalent to 3.7 times 10 exponent 10 becquerel. And we also know what is the abbreviation 10 exponent 10 stands for.
Angstrom.
Armstrong.
Armstrong. So 3.7 Armstrong becquerel is equivalent to 1 Curie. Hey, and on the more than no. Oh, I see.
It has been used. We use it frequently. So
Oh, okay. So that is it. Then we move on to decay law. Decay law. Now, radioactivity is a property of the nucleus, and consequently, the probability of a radioactive decay per unit time is constant for a given nucleus in a given state. Now, the number of nuclei that at the end that decay radioactivity per unit time is proportional to the number of nuclei. So what we are trying to say is, assuming we have a certain atom, or let's say a certain, let me bring this to our everyday activity, maybe that one you understand it well. Assuming I have 50 cedis, right? And the 50 cedis, I spend it within 5 days. And I realize each day I'm spending 10 cedis, right? Then means if I'm given 50 cedis and I'm asked to find the remaining amount in the third day, because I know the constants or the amount I spent every day, I should be able to find what is left at that or at each particular time. And
Yes.
yes, so that's why the decay law just talks about that. If you have a certain amount of a nuclei, okay, and you know the time of integration, right? Then you know the decay constant, which is the disintegration constant at any given time. When you are asked to find the number of atoms left, you should be able to know. And that's all what the decay law is talking about. Okay, so the dNdt is talking about the amount that is left at the time that you are looking for. And the lambda is the decay constant or the disintegration constant. And the n is the initial amount of atoms that it was at stake. So assuming I was having 50 units of a certain atom, and I want to find the remaining maybe in the next 10 years, and I know the decay constant, that the disintegration constant, can just go and substitute them in this expression, then you solve for it at any given time. I hope you are clear. Now we have
Yes,
this
sir.
derivation here, which is very simple, but I don't know if you should go through. Let's go through. Yes, we So here we know that the disintegration per time, the decay law is given by negative dn dt is equal to lambda n. Right. Now that's, we are talking from this one, equation 1.2. And from equation 1.2, let's take the n over here and let's take the dt here. Now let's. Is it?
No, because we make us and I make us and to the in Yasum. Hey, so we make us and then to the so we anyhow say you see.
No, the thing is, yes, I can go ahead, give you questions to go and learn and come and write. But at the end of the day, if you go anywhere and you are being asked to prove yourself, when you're A, but then it means grade near the chair or no, so they don't take you serious. You get it. But then even if you get, let's say, a C or a B, that's a bizarre question, and you're able to provide it. They know your potentials, and that's quite better than the grade. So it's better you understand it and you're able to prove yourself anywhere you go rather than just getting the grade. And that's why in most cases, you go on your first class into a baby and yes, because the things, the grade or the class he has doesn't tell you it is intelligence or his knowledge. So they be a weapon. We go our third class, then when your scholarship or yet he is doing greater things. It's all because of these things. So you need to get the concept, and that is much more important just than the grades, even though the grade also is important as far as you are in the academic environment, but you need to also understand it, and that's the prime or the main goal. Okay. So from the equation 1.2, from the equation 1.2, we just take the dt over here to the right hand side, and we bring the n to the left hand side. So they have the n over n is equal to now lambda dt, right? And we also took the negative over there. Now getting to this point, what is it? Getting to this point, we can then integrate both sides. That's to integrate the dn over dn, the lambda dt, because we are integrating this one with respect to time, and we are integrating this one with respect to n. And you and I know that if you integrate any function with respect to the function itself, you are going to get ln. So if you have the x over x, if you integrate that, you are going to get ln x. If you have 1 over a dA, you are going to get ln a. And that's why, and this is mass, and that's why happening n over here. And now, since this is not a definite integration, you are going to have with respect to a constant of which you don't know the constant. So that you have negative lambda t plus the constant, and you're having this constant because this integration is an open integration, or it's not having a limit. So you have to bring that. Now, knowing that we want to find n, we don't have to find, we are looking for n, not ln n. So in order to eliminate the ln, what do? We apply, or we introduce exponential function, that's the e. And we all know when you are doing further calculus, you know exponential times ln give us 1. So that exponential in n will go away, then you get only the n. So here, the exponential function and the ln will go away, giving us only the n. Then this side will give us exponential function of negative lambda t plus the constant. So that we have this. Okay. Now, how do you know the constants? You know the constant by substituting in a special the initial conditions. Okay, because this n that we've gotten is the n we have here, but n it's at a certain time. So n is in maybe 10 years. What will be the remaining function or the remaining atom? We don't know. So that's where you have to find out what is left at that particular time. So we substitute in the initial conditions that now I have n atoms. So when the thing have not started disintegrating, how much atom is left over there? So we substitute those conditions. So at t is equal to 0, we substitute that over here, then we put 0 over here, so that this side will go to 0. Now, if this side is 0, what will be the root of this? I don't know. Do you understand it? Do you understand the point I'm making?
No, sir.
It's quite
Yeah.
it's quite difficult to
Do
actually
you hold on?
visualize.
Do you understand up to the point? Equation 1.7.
Yes.
Yes,
Yes.
up to 1.7.
Okay. Now 1.7 is telling us the general equation for an atom undergoing decay. Okay. Now we want to find the constant, because assuming say let's take like I've given you 50 cedis. Now I said 50 cedis plus something. We don't know that something. So if I ask you to find the amount left in, let's say, 2 days time, how will you know the amount you want? Because the plus something that I added, you don't know. So you can't really do a solid calculation to tell the exact amount. But then we are looking for the exact amount that is left for a certain time. Are you following me?
Yes, please.
Okay. So then I've given you 50 cedis. I said, and then I'm this kind of amount. So what is the amount you have right now? So 50 cedis plus something. And now that's something I want to find. So I want to put in at the initial state, what is the amount I'm having? So that if I get the 50 cedis from that amount, the excess I have over there will be the plus something I told you. So that I can add it and say, oh, okay, so it's 52 cedis. So that something is 2 cedis. And how to find that is now putting in the time factor t is equal to 0 because you just give me the money. Okay. Now let's take the n of t to be n naught. And the n naught is the initial money that I know. That's 50 cedis that you've given to me. Okay. So you've given me 50 cedis at time t is equal to 0. Now the n of t here is third n naught. Okay, so if that's the case, let's put the t is equal to 0 over here. Okay, so that at the end of the day, e exponent negative lambda into bracket 0 will give you what? 1. And I'm a boy.
I don't know.
Yes, so that at the end of the day, the e negative everything goes to 0. So that I have the n, sorry, will go to 1 because e exponent 0 is 1. So that at the end of the day, you have n naught is equal to 1. So now you know the constant, that the constant over here is equal to 0 because when you add that one to this one, everything goes to 1. And hence the n of t will give you the n naught times the es for negative lambda t. Are you following?
Yes, please.
Yes, sir.
Okay. So that's how come we have this, and this is what we call the radioactive decay law. So what we have here is this, the decay law itself. Okay, and that's the same thing that it has been derived to the final point. So if you are asked to define the decay law, you can either write this or write this. Each of it is correct, but make sure you explain it to our understanding, especially the keywords in there. So example, I know some people, if you are asked to define something or any law, you just write the formulas and then say where this is that, this is that, this is that. Please, I won't go ahead and won't add something meaningful to it, because if you just say this is that, yeah, so sharp for full marks. Okay, so try and say something about it rather than just writing the formula and putting it in that form. Okay, then go on to what we call activity, and the activity is simply the process of which the radioactive nuclei is undergoing decay. Okay, and it follows the same thing. It follows the same as the radioactive decay law. Okay, this time around, just that the decay is represented by R, and that's the rate. Okay, so the same processes goes through, and I know you are going to get the same thing as we had for the radioactive decay law. Okay, but this one is the rate, the counting rates. I hope no one is confused here.
Yes, we are not confused.
Okay, so that is it. So if you are asked to define the activity or the radioactive decay law, you can state, you can just put one there. Just know that when you are talking about the radioactivity, you are talking about the number of atoms at a particular time. That's n, the initial amount, which is the n naught. And when you are talking about radioactive, the activity, we talk about the counting rates and the initial counting rates. Okay. And these are just an exponential graph to show how an atom is being decay. If an atom is undergoing decay process, how does it look like? So it's an exponential decay. That's why we have exponential function in there. Okay, so it's not a linear decay that you normally see over there. It's most often undergoing radioactive exponential decay, but then we see it in the form of a linear form, which is not the case. Okay. Then we move on to what we call half-life. And half-life is nothing but then when we are dealing with decay, radioactive decay, I said there's a time it takes for an atom to decrease or undergo radioactivity. Now, what is the time it will take the atom for half of its initial mass to decay? Are you with me?
Yes, sir.
Yes. So assuming I've given you 50 cedis. Now, what is half of 50 cedis? 25 cedis. So what is the time that it takes you for you to spend half of that 50 cedis? It's what we call the half-life. So ideally, half-life refers to the time that it takes an atom to undergo a decay, at which half of its initial mass or half of its initial quantity will just decay. So that is it. And how do we find this? As we know the activity, so that's what we have here, 1.12. You have the activity. So if you divide the initial amount by the points I've gotten to the amount there, if you divide it by that, you have to get half of the initial or half of the amount that is left. So if that's the case, then the half must be equivalent to the exponential function you're having there. And this time around, the t is not t, but rather the t for which half of the initial particle will be going off. That's why you have t half over here. Please, are you with me or you are confused?
I'm with you.
You are confused.
A little bit confused.
I said,
Okay.
Please, if you can take it again.
This is it.
Please, can you write?
Go over again for us, please.
I should go over again.
Yes,
Okay.
about the arrow bar.
Okay. We said from here, right? The counting rate is given by the initial and multiplying the exponential function times the time. Now, the time we are talking about over here is not just any time, but the time it takes the atom to reach. Hello?
We are listening.
present. We are here.
Oh, okay. I thought someone was talking. So the time here is the time that the atom have decayed to. So it could be more than the half-life or it could be less than the half-life. But then when you are dealing with the half-life, we are talking about just the time it takes the atom to reach half of its initial quantity. Okay. So that if you take the R divided by the R naught, you should get exactly half of the initial atom. I hope it's clear. I hope it's clear. So if you divide the R by the R naught, we are talking about the ratio of the initial mass and wherever it have gotten to. So if you divide wherever it have gotten to from the initial mass, you have to get half of it. For example, if I have 50 cedis and I spend the money up for it to get to 25 cedis, it means if I divide the 25 cedis by the 50 cedis, I should get half of that money. And that's what you've done over here. So that the R here is the quantity or the count that have reached the half-life. And the R naught is the initial quantity of the whole atom. So if you have the ratio of this, you should get half of the whatever that you started with. Is it clear now?
So you said that R is the what? And R is what?
You said,
The R stands for what? And the RO.
um, please hold on. I'm coming. Yes. Please come again. You said the R. Hello.
You said the R is the quantity of, and then the RO is, I was writing it, but it was
Oh, okay. The R is the quantity left after the half-life, and the R naught is the initial mass or the initial quantity. So that if you find the ratio of the amount at its half-life by the initial quantity, you have to get half. So for example, as I said, if I give you 50 cedis and half-life, it's have to, at the half-life, you have to get to half of the initial quantity. That means it have to reach 25. So that if you put the R at half-life, which is 20, and divide it by the initial amount, which is the 50, you have to get 1 out of 2. And that's why you have half over here. I hope it's clear. Please, is that clear? Okay. Now, since we are dealing with half-life, then means from this expression, right, we just multiply and divide it through by the R naught, so that R over R naught will be E negative lambda T. Okay. So R divided by R naught will give us R over R naught is equal to E negative lambda T. So that what we have over here, the R over R naught, which is equal to R must be equal to E negative lambda and the T. And now the T, as we said, is the half-life, the time it have taken for it to reach this point. Okay. Now, if you want to find the half-life, what do we do? It means you have to also apply length. Because as I said, if you have exponential function and you want to take it off, it's a matter of applying natural log, that's the length. So that length half is equal to length E negative lambda T half. Okay, so that's what is done over here. So that the length the E will go away and have negative lambda T half. Okay, and then length half is the same as length 1 minus length 2. Okay, but in some cases, we can just compute length half and you know the values. So if you know that value, you just divide it by the lambda, then you find your T half. In each way is accepted based on what you are looking for, whether the half-life or the decay constant. Okay. Now, this is a typical idea of how half-life looks like. So initially, if assuming you have this amount, then means at half-life, it takes 50% of this initial amount to go away, right? So for another half-life, it takes half of this quantity to go away. Another half-life, it takes half of this mass or this quantity to go away. Then another half-life, it takes half of this one to go away. So half-life is some way, somehow kind of technical a little, because someone will say, if that is the case, if I have 50 cities and I say, let's say, 1 minute, if someone will say, if assuming initially I have 50 cities and the 50 cities, I say the half-life of the 50 cities is 1 minute, and after 1 minute, 25 cities is gone, then means in 2 minutes, all the 50 cities will be
Ben,
right.
Ben, please mute your mic. Ben, please mute your mic. Hey, Asimo. Ben,
Let me try muting here. Okay. So as I was saying, when you are doing it, half-life calculation is quite technical because assuming I've given you 50 cities and I say the 50 cities, the half-life is, let's say, 2 minutes. So someone will say maybe in 2 minutes time, the 50 cities will be left with 25 cities. So then in 4 minutes, all the money is finished. No, it doesn't work like that. So in the next 4 minutes, it will take half of that 25 minutes will just go. So that initially, if it was 50, the next half life will be 50. Now, the next half life won't be zero, but rather half of that 50. So that it will be 25. So anytime it takes the quantity at that point as the initial amount. Okay, at any point it takes the quantity there as the initial amount and it just takes half of it. It doesn't start from the onset. So at any point it takes the quantity at that point as its initial amount, then half of it is being decayed. I hope it's clear.
Yes, sir.
Okay. So in this case, it's quite difficult for the total quantity of an atom to decay. That's why we say it's a exponential decay function. Okay. Linearity means it will be reducing in bits, but for everything to vanish is very difficult. So in most cases, you see the graph to be exponential. So it's just you can see the graph approaching to zero, but it will never get to zero because it's just half of the initial that will be reducing. So it will be reducing to a certain point that even though you feel like there is nothing, but then there's still some kind of radioactivity that still goes on there because not everything dies off. Okay. So that if you want to find the half-life, is giving us this. Okay, that's from this expression. Okay, so you have ln 1 minus ln 2 because if you see a division sign in natural log, you can just do the subtraction. Okay, so that you have ln 1 minus ln 2 is equal to negative lambda times the t half. Okay, then you have ln 1 is always equal to what? 0. So that I have negative ln 2 is equal to negative lambda half. Lambda times t half. So that if you make t have a subject, you are going to have ln 2 over lambda. L in 2 is, I think, 0.693 or something. So in some books, instead of seeing ln 2, you see 0.693 or something out of the lambda. And that's the half-life or the way to go by the half-life for any atom of that state. So either you know the half-life, you can find for the decay constant, or if you know the decay constant, you can solve for the half-life. Then if you know this, you can find either the activity at any given point or the number of uh, um, nuclide or atom left at any given time as far as the decay law is concerned. Any question? Okay. Now I have some work example, and please give me 10 minutes and go through the example. I'll be with you shortly, just 10 minutes.
your mic is on. Rikus, your mic is on.
Hey, hey.
Hello.
Yes, sir.
Hello. Sorry about that. Yes, so let's look at the question. They say 1 gram of radium is reduced to 2.1 milligram in 5 years by alpha decay. Calculate the half-life of radium. So now, what is the initial mass or the initial quantity? That's the N naught. N naught is what? They said 1 gram. So the initial amount is 1 gram. And then they said it has reduced to 2.1 in 5 years. All right. That reduced by 2.1 grams. So we want to find the amount that have been reduced or the amount that have been decayed after 5 years. It's just a matter of subtracting the 2.1 from the 1. I hope you understand it.
Sir,
Yes, sir.
please,
The amount is
sir, please
2.1
come again
milligram.
for.
Okay.
Hello, sir, Yusuf.
Yes, I'm going back.
Okay.
Now they said 1 gram of radium. So it means initially the amount of the radium atom there is 1 gram. So that's the N naught. Okay. Now they said in 5 years' time, it has been reduced by 2.1 milligram. So if you want to find the amount of radium left in 5 years' time, you just subtract the 2.1 from the 1 gram so that you know the quantity left in the 5 years' time. Madam Fisher, is it okay now?
Yes, sir.
Because they didn't say it have reduced to, once it have reduced by. So if it have reduced by means this amount have been decayed from it. So if you want to find the remaining amount, you just subtract this from the initial one. And that's why they have the N of T to be 0.9979.
Okay.
And Marcel,
Yes.
how do you subtract 1 gram from 2.1 milligram? And you will not get
You
0.997.
subtract 2.1 milligram from the 1 gram.
You get a negative. If you are subtracting 2.1 from 1, you get negative.
You don't get negative. Milli. What is the preface milli stands for?
Oh, okay.
Yes.
10 to the 12. Is it minus 3?
Yes. Milli is minus 3 and kilo is positive 3. So it's 2.1 times 10 is for negative 3 grams, which is supposing the same as 0.00021 grams. So you subtract that from 1.
Okay, so 1 minus 0.0021.
0.00021. Yes. So that
You
they,
get 0.9979.
yes, and that's why they have N of T to be this. Okay. Yes. But now we are looking for the K constants because, sorry, the half-life, but then we don't know the decay constant because without the decay constant, you can't calculate for the half-life. So if you know the decay constant, then it will tell us that, oh, okay, for each time, half of this amount is gone, or for each time, this is the amount that is being decayed. So we first have to find for the lambda. Now, the time it took from the 1 gram to go to the 0.997 was 5 years. So in that case, our T is 5. So that if you use the decay law, that's N of T divided by N naught. Or let's go by the first one so that I don't get confused. N of T is equal to N naught E negative lambda T. Now the N of T is the 0.9979. Now the N naught is the 1 gram. Now our T is 5. Now our lambda is what you are looking for. So you just make lambda the subject. So that you have N of T divided by N naught to give us this. Okay. Now, as I said earlier on, if you have exponential function, you want to take it away, it's a matter of just applying lane to both sides. So that I have lane 0.9979 must be equal to lane E for negative 5 lambda. So that this and this will go away and you get negative 5 lambda. And then lane 0.9979 will also be here. So that I divide both sides by negative 5, then you have your lambda to be this. Okay. Now, getting to know this as your lambda, you can then substitute this whole expression in the half-life expression, which we knew it was ln 2 over lambda. So that you come here and you say, then now at T half is equal to ln 2 over the lambda. Now the lambda is negative ln 0.9979 divided by 5. Then you substitute that one over here. Or from here, you can just point your calculator and get your lambda straightforward. Then you come and put that lambda value over here. Each other way it holds. So that the only the value that you get is your half-life. Meaning it takes 1,672 years for half of the radium to reduce to half of its initial amount or its initial quantity or its initial mass. I hope it's clear.
So explain the ln 2 aspect.
He said,
Explain the ln 2, where the T half is equal to ln 2 over lambda.
okay, so we've understood to this point, right?
Yeah, I understand to ln is equal to ln to like 0.997 equal to negative 5.
Okay. Now, if you understand to that point, we said half-life is always given by ln 2 over lambda, right? Yes, so that when you come here, T half is equal to ln 2 divided by the lambda. Now, the lambda is what you have over here, which is negative 0.9979 divided by 5. So they substitute it over here. Or if you don't want to confuse yourself, when you get to this point, use your calculator, punch it, whatever value that you get, you just come and write it over here, and you just compute it. I hope it's clear. Okay. But in some cases, it's always advisable, as I said the other day, to use the parameters in this thing. But in this case, you can just go ahead, write the lambda value, then you come and substitute over here, rather than writing this. Because I'm saying this because sometimes the question, you see that for this question, they didn't ask of the decay constant. But in some scenarios, they will be marking the decay constant before marking the half-life. So if they don't see the decay constant value, you lose marks over there. Assuming it's 1 mark, you lose the 1 mark over there. So when you get to this point, just compute your final answer and write it there. Then you come back and solve for your half-life. Okay. There's another example over here, which I'll leave that one for you. Then we move on. But it's still the same thing, the same idea, the same ideology. The same idea. Even this one, you are given the half-life. So it's not something new, something difficult that you can do. It's as simple as that. Then we go to what we call mean free time. Mean free time. And since individual radioactive atoms may have lifespan between 0 and infinity, yes, as I said, when you are talking about radioactive decay, the thing seems to approach infinity, 0, but it's not 0, it's getting to infinity. So always take note. Okay. We can then talk about the average life of or mean life. We may determine the average life expectancy of atoms of a radioactive species. That if you have an atom, you can find the mean free time or the mean life for that species that you are dealing with. This average life is found from the sum of the times of existence of all the atoms divided by its initial number. That's assuming if the atom have undergo 1,000 decays. So you just sum all the 1,000 decays, then you divide by the initial mass or the initial quantity, and that should give you the mean free time. And then it's also given by, we represent that by tau, and tau is given by 1 over lambda, where the lambda is the decay constant. So take notes. The tau is equal to 1 over lambda. So note that all this is just to show how they arrive to this point. But then I'm not going to ask anyone to prove this thing to me. So just note that in a question where you are asked to find the mean free time of the average time, is given by 1 over lambda. Okay. Mr. Francis.
It's okay. I wanted to ask the mean free time is 1 over lambda.
Okay.
So is T is equal to 1 over lambda.
Yes, T is equal to 1 over lambda, but it's not just T, it's tau. So take
Tau.
note. Yeah.
Okay.
So that is also that for that. Then we move on to, and please, you see there are some objective questions here. That even reminds me. I think I was going through the book. Was it somewhere within the week? I don't know whether it was this one or the EM field. I realized they've underlined some of the answers for you guys. Or it's not this book.
It's this book.
Is this book?
Maybe sir.
Felicia did that, eh?
Pasa Fanua Bra quiz in my way, Patchua.
Oh, God, Felicia, Felicia, I'm going to Felicia, and I said Felicia, and it's all me.
And you know, and I don't know about the chemical.
Oh no! I was to be frank. Yesterday I was very tight, very very tight. Sorry about
As
that.
I'm saying, the queer pie first week, you put it back up. The queer collapse a first week, and then the any bigger bomb. We are nobody, I know me. 15 year child, and one, a bit for the rest.
Now, I don't want your quiz now. How long does it take for you to get your papers?
It's about 4 days now. Money about to a would the open one or max or score. Who say we will try. Shame.
You guys are also part. You guys are also part. Some way, somehow, I won't blame code for everything. You guys are also part. In the sense, which your quiz we are, at least you have to demand for your paper. Why am I saying this? Because
Sir, the quiz is online. Sir, the quiz is online. It's not written.
Yes, so you can demand for
It's
your
done
script.
online. It's done online.
That's what I'm saying. You can demand for your script in such a way that questions now I'm solving or quizzing, at least 50% of them will also come in the exams. Now, a quiz, no, I can find within when you say correct. No, as I can find that same answer or exams.
And
No,
yet,
so you need to come them.
So we've been telling them, but they are not giving us the reply. That's the situation. They are not giving
Anyways.
us
Yes, there are some hands up. You can go ahead and talk.
This particular question, the last time we had a junior forum, I made this is not something that we have not said. It's not something that we have not said, but you know your people. So it's not that we don't know or we are not asking. We have been asking. Last time I told them that if the essence of the speech is not to fail us, then they should give us the result. Let us analyze it so that when we, even if not exams, when we see the same question elsewhere, we know that this one we know. They don't do it. So sometimes what we do is that we try to write them, and we get images and we give it 20 minutes to solve. So if you're able to write it, sometimes we write 2 or 3 of them. From that is the best we can do. So it's not that we don't want to. It's not that we don't want. That is how they have reduced us to just pay the money and let's give you 10 class and go.
Anyways, because I sometimes feel so listen. Because my chemo papers are objectives no someone could get as low as a single number, and I'll be like, the questions no who now because obviously sometimes a quiz questions never. So even if you've seen these questions before, at least you should be able to resolve it so that when you come there, you'll be able to do your best. But then you still be, anyways, it's all good.
Code right,
Right, sir.
Psychology and a hard copy. Or go by first quiz, second quiz. Go through all the people, first quiz, second quiz. End of semester. This is why we have to do. go through one year, 50-60% you'll be from the previous year. But
That's
here
what
by
I'm
the case,
saying.
you just release the score. Send it on so what any young coupon.
But at least, say I am the questions in Samamu.
Like, don't go away.
So we don't
Online,
get
no,
anything. No. You do the thing online, and when you finish and submit the results, you submit the
it's difficult
answers.
for me to.
The screen will just tell you a review is not possible. Even if you want to review like and see how you know what you scored and which questions you had, the screen will tell you that the review is not possible. So and then sometimes to the questions, especially the calculations one, the time is just too insufficient because you have 20 questions in sometimes 21 minutes, and then there are calculations. And with the online thing, they don't, as we've been saying, they don't provide any constant. At least with the paper, sometimes they may provide the paper the constant, but with the online, nothing, no constant at all. So if you don't know the constant, then you'll be there. So these are some of the problems that we face during the quizzes.
And then we trap 4, 5, 6, no. And then be and no.
Yeah, so you see that
You just skip, then you move to the next question. No.
you see that with
Shabuwa.
this one, what we are just is not the true reflection of our performance at all. It's not a true reflection of our results of our performance at all. They are just collecting our money and giving us class. They know. I don't know whether it is a compact program. They don't want you to pass, or they don't want you to get a very good class. Like I mean, that is my feeling. But if you get a very good class, then you see that course. So it's like they are
It's
pushing you in
true.
the corner. They are pushing you
It's
in the
true.
corner to get your third class or your second class upper lower, so that you see that you will know course is not difficult. Because I know those doing the same course distance, those who are doing it for years, they don't go through this action. Why will you give somebody a quiz to write, then the person will never see the result? You go and meet the same thing during the exam, and he will fail the same question. And as of now, I still don't know whether that question I know it or I don't know it. Because if I meet it somewhere, what I selected. So if I just imagine I'm going to teach, and the students ask me such a thing, say I'm not going to do this for something that you are supposed to learn. You didn't know the answer. So me, it's difficult for me to recommend someone to come and do this course. Me, it's true. I won't because if I recommend, the person will end up blaming me that why did you allow me to go through this punishment? It's punishment. Somebody write the exams, you will never see his score. Those who did it last year, they were giving their results. They were doing it hard copy. If you can't give me the result, then let me do it as copy and keep my results for at least future reference.
It's okay. It's all good.
Hey, bro.
Me like this.
Wallahi,
Me like this. I'm not. I have nothing to do with them. My own is I've been asked to teach you and I'm teaching. But then sometimes I feel like some of the things are not right there. And probably maybe it's because it's a new program. They'll just put things in order for it to be quite better. So don't worry, Shabua. Shabua. At least here though, yeah. Lab rats,
Said all the time they said it
yeah,
shall be well, but it has never been well.
Say,
Said
it shall be well,
they
it shall
say
be
all
well.
the time
So
it shall be well, it shall, but it has never been well too.
it looks like
it has been well.
it shall be well,
But it has
sir.
never been well too, and we are still suffering. Hey, it's right there, dear.
hey, nah,
Thank you.
no, me there, I'm just trying to give you guys morale. Me there, I have no
It shall be
idea
well,
what
India.
to say.
Now, Mr. Isi, it shall be well, original.
No way.
So, I am a
Do
young
you know
why
something?
third class and the pass, yeah. And it shall be well, wow, Mr. Isi.
Yenya ye TV o ye boss ku mu afoforo ye kra some dey say shabo ye ka che say befa some that's one so normal. Sometimes you just have to go through some of these things so that you know how strong you can endure some of these things. Okay. So I
It's true.
think
It's true.
in
Yeah,
UTC, it's not
fine.
only about academics, it's also about your perseverance, how strong you can take some of these things so that when you go out there, you'll be able to withstand anything that comes your way. So, in as much as they are treating you this way, yes, you know it's not fair, but then it's also building you for you to be strong. Because when in the you say course and when in the can be brave, it can
Ah,
affect
let's
Say,
say
life.
me be
ebi ejai.
be
So that is
Ah,
it.
say
Bebrebe.
It's
eh
had
eh
a
eh
that's what because of your
eh
perseverance, and it's also part of the
ah,
training process. So you have to take
say
it like
our friends when we meet to discuss questions, yeah, I say I did new concept. But with the help of AI, we are trying our possible best to get the answer. Tiny in them with our assemble.
Eh,
and I'm also more can be more groups and more tutors in our if say questions be about now, you can just DM your lecturer now and people will say my own question means I say lecture be any
The
some
concept
question.
now,
hey,
one of the question.
you
One
see,
your concept
they
now.
don't have time. Oh.
You don't have time.
Our lecturers, you are doing a lot of things.
Yes, we are doing a lot of things, but I know I'm teaching you in this course and you brought something on board you don't understand. Why won't I help you? Or will I be happy if you go and fail? No. So I'll just help you. Even if
Sir,
I'm busy, you have to find time within my
Actually, na call actually na call na
our
question
posters
na.
our
Yeah.
posters have got a program since we started this course, and they have not solved it. And you think that they will have time to solve a single question? Eh,
Eh,
Poster
ofi
like
ye
Obiato,
bro. Na actually no sa fight na person.
as I told you,
Na
I first semester, first trimester course. The resolving man. Obi wo me say course that me register, I be added to my course. Because I will get it. And they've not solved this one. And so you think that when you tell them that they want to solve a problem, first they will solve it for you. The whole program cry you are failing. What one person is solving do for you there. So I'm not sure we don't even try because they have disappointed us elsewhere. They are disappointed us, so we don't even try. And those who left, say it's because they can't bear injustice. It's not that we are persistent. We can bear injustice. They are not being first one, but we can continue. But those who left, they can not bear injustice. So they've left the program. I mean that is what I mean. It's not that we are persistent.
not sure. Maybe.
Thank you, sir.
All right, let's move on. So we move on to radioactive equilibrium. Radioactive equilibrium. And if you are talking about radioactive equilibrium, I'm just talking about um, a point where the atom which is undergoing radioactivity has come to a halt or have been in a stable state. Okay. Now, it is a natural to ask how one can measure a very long and very short half-life. It is obvious that the equation n equals n naught e lambda t cannot be used for this purpose directly. Help comes from the fact that the embers of radioactive decay series are radioactive. So the embers of radioactive decay series are also radioactive too. Generally, the number of daughter nuclei is changing with time as well. Hey, please mind you, I didn't mention of daughter nuclei. If you talk about daughter nuclei, that means an atom undergoing radioactivity, a splitter, a decay, the acanefeno, daughter nuclei, and a parent nuclei, the initial win. So take note. This will continue until the decay rate of the radioactive product, that's the daughter nuclei, becomes just equal to its rate formation from the previous member of chain, that's the parent nuclei. This condition is called ideal equilibrium. We consider a brief special case in which the radioactive daughter substance was formed in a decay of the parent. Let us take the general case for the decay of a radioactive species, denoted by subscript 1. That's for the first species. To produce another radioactive species denoted by subscript 2. So the first one, which you can term that as the parent, is 1, and the daughter is 2. so that the decay law for the parent is this and the daughter is this. Now, the second species is formed at the rate at which the first decays, and itself decays at the rate of that's the 2, so that we can find the decay law of the second one as that. Because if you subtract this the daughter from the parent, you should get the initial mass, the mass of the second one that is decaying in respect to time. So that if you substitute the n, which is this, into the expression, you get this. Let me just move on. I won't be bothering anyone with these things. But then what I would like you to know is what we call transient equilibrium. We have 3. So let's look at them. Now they say in equation 2.11, which is this. They said in apply equation 2.11 to considerations of radioactive, that's parent and daughter pairs, we can distinguish 2 general cases depending on which the 2 substances have the longer life. Now, if the parent is longer lived than the daughter, so you are talking about radioactive decay, right? Initial atom, and it have decay after a certain time to get to the daughter atom. And he said if the parent, that's the initial mass, lived longer than the daughter atom, then that state is called radioactive equilibrium, or it has reached a radioactive equilibrium. But then with that, we also have types. Okay. A state is so-called radioactive equilibrium is reached. That is, after a certain time, the ratio of the numbers of atoms, and consequently the ratio of the disintegration rates of parent and daughter becomes constant. So that the transient equilibrium, you realize the ratio of the daughter to that of the parent becomes the same, or it's in equilibrium. They are all the same, even though the parent atom is longer lived than the daughter. Okay. I think I have a summarized notes on this. Where do I have it? I think I have a PDF file, a PowerPoint file that summarizes all this. I will look for it and get it for you guys. So when you talk about a transient equilibrium, you realize the parent atom is this one, right? And as you know, the daughter is always gotten from this, from the initial onset, it decays to this point, and at a certain point, they all start living together. I don't know if you understand it.
Please come again.
Okay. We said when we are talking about the transient equilibrium, right? The parent is longer lived than the daughter, right? But then it gets to a point where they are all in equilibrium. It means they are all living in that same time. The half-life, they all decay in that same time. So, for example, assuming if I'm having, let's say I have 50 cedis, right? Because this amount is high, boom. But then, so now you become wiser. The spending now reduces. Okay. So the initial amount is what we are calling the parent. Now, to a certain point, the daughter will say, oh, she said the scanner is say using a wiser. Then we said it has reached equilibrium with the parent. So that at that point, the spending between the initial one and the what the consideration it's more or less like the spending almost the same. Thinking about, let's say, the future. I don't know if it's understood now.
Yes, sir.
Okay. So when you are talking about, we talk about the transient equilibrium. So with the activity, always the daughter starts from the origin or from 0 to the point that when it gets to equilibrium position with the parents, they all start decreasing in a constant value or in a constant rate. And that's why you see the daughter first starting from this point to that point. So when you get to the point where the parent atom is also depreciating or disintegration at a constant value, they all start disintegrating at that point. The part we have what you call circular equilibrium. So the transient, the circular, and then I think the case of no equilibrium, I will get to that notes. We talks about all of this, then maybe we talk about that one. So let me just skip this point. Then go to what we call alpha decay. Alpha decay. Now, alpha decay is nothing more, as we all know, when you talk about alpha, what are you talking about? Minimal, when we were starting, we talk about alpha, beta, gamma.
Energy emissions is emissions.
Which is likened to the hydrogen nucleus.
You said?
Alpha particle deal with radioactivity.
No, alpha decay is a decay of a nuclide to releasing an alpha particle and energy.
And what is alpha particle?
I thought you was asking for alpha particle.
Alpha particle is a helium nucleus.
Helium
With
atom.
2 protons and 2 neutrons. A helium nucleus containing 2 protons and 2 neutrons. Oh, I think
yes.
I don't know if what I'm saying is clear, whether my sound is okay.
Yes, it's clear.
Yeah, so I'm saying that alpha decay, that is a type of radioactive decay in which the parent nuclide or decays into a daughter nuclide or nuclear and then releases an alpha particle. And the alpha particle is a helium nucleus. It contains 2 protons and 2 neutrons.
Okay, we take it that way. We take it. It's correct. So in that case, as we said, when you are talking about radioactivity, it's a matter of an atom decaying for it to be stable, and in the form of decaying, it releases some form of products or particles. And if we talk about alpha particles, then those are the particles that is being eliminated as far as the radioactivity is ongoing. So those are the energy that is being released from the atom for it to gain the noble gas configuration. So nuclear radiations can be well referred as ionizing radiation because they are sufficient energy to cause the production of ion pairs in the medium which they pass through. The more common particles usually emitted are beta plus and beta minus and alpha and gamma particles. But now, do you know the difference between ionizing radiation and non-ionizing radiation?
Ionizing radiation is the radiation that gives out the various particles, that is the alpha particles, the gamma particles, the gamma radiation and the alpha radiation. And those type of ionizing radiations are the ones that can harm the body. That is, they destroy tissues. But for non-ionizing, they are the ones that are found in the radio cells, the infrared, the radio waves, and the rest, and they do not harm the body.
Okay. So that's correct. So when we talk about the ionizing radiation, the energy is very high that they can cause mutation to the cells, but non-ionizing radiations are not that strong. They have a less energy and less frequency, so they can't really come. But even though long exposure must also have impact on our body. So I'm going to alpha particles. And we said alpha particles can be stored by a thin sheet of paper. This is, I know you've done it, you did it in DHS and SHS. And two, they can cause intense ionization
DHS
in air.
Anyway, so we did it in nuclear and environmental physics, but GHS, we don't do radioactivity in GHS.
Okay. Yes, all right, Mr. Sammy.
Yeah.
Okay. And they said they're making a matter that.
Oh yeah. So for this one, we know the alpha, beta, gamma particles and their properties. We did it in the.
What name am I escaping?
So you wanted to focus on the parts that are coming, so that's because probably from today we'll be writing the quizzes, so like you make what?
I think that is better.
Hello, sir.
Some of the things we have already done it though, but they are just minute changes like formulas and stuff that are a bit different from the one that we did in nuclear physics. So if you can focus on that one, not as necessarily the questions, but the aspect of those ones, then we can go for it. You say next 2 weeks now. I can't not just say.
Finally, Mr. Castro so can be said the eba. Hey.
So you see that we make one do. For 1 year.
Grace number the catch with the name of my say, not necessarily but now. Uncle straight to the point. Dear banana say, I'm doing ready one last hour. Don't we and I, yeah.
Say, Yusuf, because it's true. And no matter your coach secondary school for the yes, all these we've learned them before, so and yes, you know. This final 4 weeks there because November 15th we are writing quizzes. Now the following week exams. That's just we into it.
Don't worry. As I said, don't worry. Definitely, it's not going to be something.
The stress is not too much. It's not easy. Say, what class?
That's why I said, don't worry. As far as Dr. Charles is concerned, you shouldn't be worried. At least, don't worry. As I always tell, don't worry. Everything is going to be fine.
Don't worry about a thing.
I
just said you are going to be in front of her.
Thank you, sir.
Okay. So let's move on. So point 2, they cause intense ionization in air, and also a group of alpha particles emitted from the same type of nuclei usually have definite velocity and energy. And alpha particles also cover a definite distance in a given material, practically without any loss of intensity, and suddenly in a small distance are absorbed completely. Now I move on to alpha decay. So alpha decay is nothing but then when you take a radioactive nuclei and you take away the helium atom from it, at the end of the day, you are going to get that alpha particle. So let the radioactive nuclei X of AZ be called the parent and have mass M, so that the mass times the parent nuclide is given by M into brackets A, Z, and that of X. 2 or more products can be produced in the decay. Yes, so if this is undergoing decay, 2 or more products can be produced. In the case of 2 products, let the mass of the lighter be the mass. Let the mass of the lighter one be My, and the mass of the heavier one, normally called the daughter, be Mg. Now the conservation of energy is such that M of A is equal to M of D plus M of Y plus Q over C squared, where Q is the energy that is being released after the reaction, and it's also known as the kinetic energy. Okay, so that when you add the whole of this, you have to get back to the initial mass and then the parent nuclei, so that if you add the daughter nuclei and the byproduct, or the let me say the byproduct, and that's of the energy that is being released, you have to get back to the same thing. Now, the energy is given by this. The energy, that's the kill. And we also call it the disintegration energy is given by this. And we are doing this because all what we have in the square bracket stands for the mass defect, or the mass, which is the M. So that we have the mass of the parent nuclide, then you subtract that of the daughter nuclide and that of the lighter nuclide from it. But please mind you, this, the MD and the MY is all in brackets. So it's M of this minus into brackets MD plus that of MY, or M of this minus MD minus MY. I hope you get it, because the mass we are dealing here is the mass defect. It's not this mass, as in the negative is affecting the MD and the MY. So take note of that. Okay. Note that the disintegration energy, Q, is the negative of the binding energy. Yes, the Q is the negative of the binding energy, because binding energy is the one that put them together. And the binding energy is the one that is separating the excess from the nucleus. So if the binding energy is the one putting them together and it's positive, and the one taking them off is the negative one, because as you know from vectors, negative is a direction. So if this is coming in, that means the negative will be the one to separate it. Okay. The binding energy normally refers to stable nuclei. As we said, when we talk about the binding energy, it's normally referring to a stable nuclei because it holds them together, and because they are all, the number of protons is the same as the number of neutrons.
Hello, Mr. Yusuf.
Yes.
So from Q is equal to the square bracket M of X. You are saying that the MD plus MY should have been in bracket.
Yes.
Okay. All right.
Because at the end of the day, is this one that is giving out this. Okay.
Yes.
So now if you want to balance the equation, it means we have to subtract this from this and subtract the MY2 from this one. So it's
okay.
MX minus MD minus MY.
All right.
Yeah. So the negative here is affecting both the MD and the MY.
D and MY. Okay. Yeah. All right.
The binding energy normally refers to the stable nuclei. Here, as Q is normally used for unstable nuclei. If B is greater than 0, a nuclide is bound and stable, and if Q is greater than 0, a nuclide is unbound, unstable, and may decay. Looking at natural abundant radioactive nuclei, we find that decay-emitting neutrons do not occur because the masses are such that Q is less than 0. If neutron decay were possible for the radioactive nuclei, it would have taken place too quickly for the nuclei to be naturally abundant. I think there's no need to even talk about this. Now let's look at the alpha decay. Now for the alpha decay, let me go through because I can see the energy here. As it has been pointed out in the last session.
Yes. Hello, Saisi. Please, I want to ask permission to leave. You're having some family funeral, so it's not my intention to leave. Okay, thank you.
Yeah. So, as it has already been pointed out in the last session, one of the ways in which nuclei decay is by emitting alpha particles. Yes, alpha particles are generally emitted by very heavy nuclei containing too many neutrons to remain stable. So as I said, a particle becomes unstable if the neutrons are many. And this occurs as a matter of being either more neutrons than the protons or more protons than the neutrons to make it unstable. And in the case of becoming stable, it releases some of them. And the excess of some of the energy released are the alpha particles. The emission of such a neutron cluster as a whole rather than the emission of single neutron is energetically more advantageous because of the particularly high binding energy of alpha particles. Radioactive decay may occur for a nucleus when some other combination of the atomic mass nucleus has a lower mass. In other words, the combination of 2 neutrons and 2 protons is particularly stronger than of the pairing effects. So as we said, if you have 2 neutrons and 2 protons, they are much stronger, very, very strong. And I remember you also said when the proton and electron are more than, I think, 20 or so, the atom start to behave unstable. We mentioned of that, which we have a graph that depicted that. Okay. If the last 2 protons and the last 2 neutrons in the nucleus are bonded by less than 28.3 mega electron volts, then the emission of the alpha particle called alpha decay is energetically possible. For alpha decay equation, we have this. And why do we have this? Now you have the atom here, right? The unstable atom. That is the X. Now, we said at the end of the decay, at the end of alpha decay, we are going to get an alpha particle. And the alpha particle, as we know, we said is a helium atom. It means if you subtract the helium atom from the alpha particle, you have to get the daughter nuclei and the energy that is being released. So if you take Y will be the same as AZ, but then we are subtracting 4,2 from it because the 4,2 will stand for that of the alpha particle over here. So that if we take the alpha particle and even leave only this, we have to, something should prompt you that alpha decay is being observed in this reaction. Why? Because the 4,2 stand for alpha particle. And if you are subtracting from it, then it means we have alpha decay going on there. There we have our QA. The QA is the disintegration energy, or the energy that is being released, which we said most of the times is always the kinetic energy. I hope it's clear.
Yes, sir.
Okay. Then go on to energy of alpha particle. Okay. Energy of alpha particle. One of the quantities of interest in connection with alpha decay is the energy of alpha particles emitted in the decay process. This energy is measured by what is called a magnetic spectrograph. In a magnetic spectrograph, a magnetic field is used to make the alpha particles move in a circular path. By measuring the radius of the circular path, the velocity of the alpha particles and hence their kinetic energy is determined. And this also work or is also satisfy the velocity selector thing, which is have we spoke about velocity selector before or a cyclotron?
Yeah,
Yes,
we did
yes. Last time we talked about
we did
it.
it.
So it's the same scenario. Okay. So now when the alpha particle is undergoing a circular path, this is the force. That's for centripetal force, F is equal to mv squared over r. Okay. And now here is the point where it's being treated like a charge which is in the magnetic field, which has 8 QV. So that you make V the subject, you get this whole thing. I hope you are making sense. Now, K is the charge of 2 protons. Ma is the mass of the helium nucleus. From this, energy is given by that. So we know from kinetic energy, A half energy is equal to kinetic K is equal to half mv squared, right? Now the M we are talking about is the mass of the alpha particle, and then the V is what we've gotten over here. So if we square everything here, we have this, and that will give us the energy of the alpha particle. Is it clear? And answer means uncle over the equation is to be.
So that equation, the mv squared over r, that is the centripetal force.
Yes.
And the H Kelvin, that is the magnetic force.
Yes.
Causing it to deflect.
No,
So the
yes,
H,
and about that, you see, it's first moving from the electric field. So from the electric field, not electric field per se, a velocity selector. So it's arrangement of both electric field and magnetic field, which is perpendicular to each other. Okay. So you have to take in in consideration the charge, the strength of the field, and also the velocity at which this charge is moving with. So the H is for the field strength, and then the Q is for the charge of the alpha particle, and the V the speed is moving with.
The velocity.
The velocity. Okay.
Okay.
So from there you make V the subject and you get equation 3.4. But we all know that when you are looking for kinetic energy, it's half mv squared.
Mv squared, okay.
Now the m we are talking about is the mass of the alpha particle. That's why you have m alpha.
Okay.
And now the v squared, we know v is given by this. So it means you can substitute this v there, but then it's v squared. So you can square everything here so that you have q squared over ma squared, then hr. Now we have ma here already. So if this one is squared, means this will cancel one of that, so that I have only ma. So they have q squared over ma, then the h squared and r squared. Where the r is the radius, the h is the field strength, the q is the charge, and ma is the mass of the alpha particle. Are we good?
Yes, sir, we are.
Okay. And the energy is usually expressed in mega electron volts. So in spontaneous alpha decay reaction given in that of the equation 3.3, the mass of that of the dot, the byproducts and that of the velocity must be equal to the mass of the alpha particle and that of the velocity of that, which we all know is for momentum, because momentum is the product of mass and velocity. So if we are saying it's undergoing alpha particle, then conservation of momentum has to be obeyed. That's because if you take what is the decay? Yes, if you take this, right, this and this, so it means when you find that of this and that of the alpha particle, it means the momentum has to be, the conservation of momentum has to be, because everything here must come after everything over here. Okay, but here the atom is not undergoing any collision, or it's not undergoing any spontaneous emission. It's when it comes to this point, that's where it's going under emission. That's where you have the daughter nuclide and the byproduct and that of the energy. So this point is where the conservation of to be, so that when you put all together, in addition to the daughter nucleus or nuclide and that of the energy produced, you have to get the same thing as that of what we are having over here. And that's why we said the h of the myv must be equal to the m of the alpha particle and the v of the alpha particle. Also, from conservation of energy, that's when you take the energy of the alpha particles, also this also holds. This also holds. And I don't know if I should even explain this. Everything is in that order, and I don't know. There's nothing for me to explain. It just goes through the same process, but then don't stress yourself. As far as this is concerned, don't really bother yourself about how we came about all this. Just know that for alpha decay, the disintegration energy is given by half mv squared, where the m is the mass, the v is the velocity. Of which this one you know already from crown crab, brim crab, YSR, so you know. Now they gave us some work example. They said take m equals to this, and now the m, that's the mass of the uranium atom, that's the parent nuclide is given by that, and that's of thorium, which is the daughter nuclide, is given by that. And then the mass of the helium atom, it means it's undergoing alpha decay. That's why you have also the alpha decay to be that. In the alpha decay equation, so you have this mapping onto that is the deuterium plus the helium plus the disintegration energy. It said calculate the energy of the alpha decay by the uranium. So as you know, so from the top there, what I was saying is the m of this minus that of that minus that of that. As I said earlier on, just here. So it's, you see, this is the reaction. So it's this minus that. So this here is negative. That's why when it come here, you have the m of u, and the m of u is this one, minus the m of t, which is this one, and the m of the alpha particle, which is this one. Okay, so that we get all this. Now m of u and everything is given in the question, so you just substitute them in the question, and at the end of the day, you just get your disintegration energy. I hope it's clear. It's not difficult, so it's just a matter of substituting the values.
Yes, it's clear.
It's clear.
Okay. And mind you, I hope you know where this is coming from. That's the c squared. Okay.
Yes, sir.
Then we go on to absorption of alpha particles. Absorption of alpha particles. As alpha particles pass through matter, they lose energy almost entirely by collisions. Brownsing is negligible, while radioactive loss may not always be negligible. The number of collisions and amount of energy loss in alpha particle is subject to statistical fluctuations, and so all members of initially monoenergetic beam may not have identical ranges as they pass through an absorber. Then we go to ranges of alpha particles. So if you take alpha particles, they all have the limits they go, or the range at which they can exceed. So when you take air, alpha particles can travel in the for a distance of 6.753 per second. So if you take air, there is the range of which alpha particle can go. So in a second, it can travel 6.953 centimeters. When you take aluminium, it can travel in aluminium of length 0.00406 centimeters in a second. So they have all their values over there. And then we go to the actual relation between the number of particles and the distance from the source. And you show in the figure 3.1. So we have also this, which you don't have to bother yourself about this. I hope you can. What's the difference between the N naught and N naught on 2?
Then notice the mass before integration, and N naught over 2 is after the first integration, the first half-life decay has taken place.
Exactly. Yeah, exactly.
Okay. Don't worry yourself. I just wanted to know if you can just look at this picture and tell me something. That's all. So you need not to worry yourself about these things. Okay. Then move on to beta decay. So you spoke of alpha decay. Now you have to also come to beta decay. And what is beta decay?
That is the decay of a nuclide into another nuclide, releasing beta particles, and beta particles are electrons.
Yeah, okay, that's all what I want to hear. So beta particles are always electrons. But have you heard of positron before?
Yes.
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 When I'm catching man.
No, it was part
nuclear
of the nuclear, yeah, the one we did last block.
Nuclear environment.
Okay,
Yeah.
so what is a positron?
Actually, we just learned that it is released alongside like the positrons and the antineutrinos and the neutrinos. Yeah.
And we also. Okay, go ahead.
They were released along the various particle radioactive decay along with their particles. So that's what just we learned, but we didn't really go into it. I don't know. Someone can help out.
Yeah, the beta
Hello,
particles,
hello,
we have two types. We have the beta positive and the beta negative. So the beta negative is a normal electron, the negatively charged electron. And the beta positive is the positron, that is a positively charged electron.
Yeah, that was all what I wanted to hear.
Yeah,
That's all what I wanted to hear. Thank you. So when you talk about a positron, it's a positive electron. Okay. So let's look at some of the properties of a positron. So they cause less ionization in air. They are 100 times more penetrating than alpha particle and can penetrate a sheet of aluminium a few millimeters thick. And a particular beta active element emits beta particles with energies varying between 0 and certain maximum. The maximum energy is called the endpoint. So if you are talking about beta particle, it can penetrate a certain distance or have an energy varying from 1 point to a certain distance or a certain value. And then the value, the limit of that value is what we call the endpoint energy. Now we talk about beta decay. Beta decay. The emission of negative electron, beta negative, a positive electron, that's positron, or the capture of an atomic orbital electron, EC, is called beta decay. So if you are talking about beta decay, that means after the reaction or after the decay, either an electron is being released, a positron is being released, or what we call the electron capture is being released. Okay. Another way in which, so when you are talking about beta decay, we have three scenarios or three cases. The first one is a positron, electron. Second one is a positron, and the third one is electron capture. Take note, under beta decay, we have three reactions or three processes where you have the electron, the positron, and electron capture. So for the electron, always electron beta minus is being released. For a positron, always electron positive is or beta positive is always released. Electron capture, always it capture electron in the reaction, then it helps it to bring out the byproducts or the daughter nuclei. Okay. So as I said, there are three types of beta decays, and these are the negatron. So when you take the negatron, always the neutron, right? It releases a negative neutron or beta. The neutron always releases a negative beta or beta minus, and positron always beta positive is being released. As I said, so negatron, always the neutron releases a negative electron or a negative beta, or positron, a positive beta is always released. And then electron capture, realize initially the atom captures electron and then it brings out its product. Please take note. When I'm talking about the negatron, which is a negative electron, always the byproduct is that of the atom itself and also an electron. Please, are you here with me?
Yes, sir.
Yes, please. Yes, please. You are following.
So the negatron always, apart from the product is being produced, we get an electron as part of their products. That's a beta minus. And positron always get a beta positive. That's a positron. But when it comes to electron capture, the atom that is undergoing that decay is being captured by electron or is being added with the electron as the reactant. Then it gives out its product. So the negatron and positron, always the electron and the positron are byproducts. But for the electron capture, the electron is part of the reactant.
Okay, sir.
Okay. Then we go to that of the beta emissions. The beta emission just has the same way we did for the alpha decay particles. The same way. So there's the parent nuclide and there's the daughter nuclide. But then because you are having a beta negative, you subtract that electron from the atomic number and you have to get a balance equation. And yes, all the things also the momentum, conservation of momentum, conservation of energy, everything. So the same thing holds for this one as well. And you can also go that and do all what we did for the but rather will be a machine. Okay, we can go through the same process and to get to that as well. But don't waste your head or don't worry your head more about this. Yeah, Mr. Samuel. Sorry, Mr. Francis.
So you can hold on, it's okay.
It's okay.
Yes, please.
Don't worry yourself about it until it's okay. Hey.
Oh no, I wanted to ask a question, but it's like you have answered it. That one was really for concerning the negatron, the positron, and the electron.
Oh, okay.
So I'm on.
Okay. So this is it, and the release of energy in this kind of processes is what we have over here. So if you have an atom is undergoing some of this decay, these are the processes it undergoes. So the first one undergo this kind of emission, and it undergoes. So assuming it's undergo three, let me say 3 half-life. So the first one goes this way, the second one goes this way, and the third one goes this way. And that's typically for AU undergoing through this decay process to give you AG. Right. So these are the energy that is being released at the end of the process, of which factor and how baba it won't help you. Don't stress yourself about this, as I said earlier on. Then go on to energy of beta negative particles, just as the same we did for the alpha decay. The same process is what we go through. Then we have that. Then we have absorption of beta particles. And the range of beta particles is larger than the range of alpha particles. While alpha particles have a range in air of only a few centimeters, the range of beta particles in air is about 1,000 centimeters seconds. That beta particles would have to be absorbed by a medium like aluminium. The reason for this is because when they pass through a medium, beta particles create less ionization than alpha particles. But while alpha particles get absorbed or lose their energy by only ionization, alpha particles lose their energy by X-ray emission, that's the Brownston and breaking radiation. The loss of energy by Brownston is more significant for absorbers of the heavier elements. In general, the ratio between the loss of energy by ionization and the loss of energy by radiation is given by that, where Z is the atomic number and the E is the energy. Z is the atomic number and the E is the energy. Okay, so the rate at which the energy is reducing, the distance with respect to the radiation and that with respect to the ionization is given by this. Please don't worry yourself. Okay. In general, the absorption of beta particles is also exponential. The absorption of beta particles is also exponential. Thus, the N of S is equal to N naught E negative mu S, where the mu stands for the absorption coefficient, and the S is the distance at which this particle is being traveled, or the point at which it has reached. Okay. Yes, I think I have to talk about this. The distance of the absorber when the radiation of beta particles equals the background radiation is the range of beta particles in the medium. That's R beta. as would be expected, the range is related to the energy. The empirical relation between the range and energy of beta particles is given by what we have over here, where E naught is the endpoint energy of the beta particles. The two curves, that the two straight lines, are referred to as Sargent curves. The upper curve is the curve for what we refer to as allowed transitions, and the lower curve is the curve for what we refer to as the forbidden transitions. The terms followed and forbidden are to indicate that one type of transition much more probable than the other. The theoretical approach to study beta decay is a theory that is referred to as the Fermi theory of beta decay. Have you heard of the Fermi theory before, the Fermi principle?
Yes, please.
Okay.
Yes.
Okay, thank you. In this theory, the emission of beta particles is supposed to be as pointed due to reaction. So we have that of the negatron. That's and then you are going to get, I'm sorry, positron. And then you are going to get beta positive, and negatron, then we are going to get this. Okay. I think all this is not something we should waste time on. Shouldn't be wasting much time here. And go to what we call gamma radiation. Gamma radiation. So we talk about alpha. An alpha particle, you just have only one. That's where we have the atom undergoing just a decay, of which you have a daughter nuclei and alpha particles. And we have a beta decay. Of which the beta decay, we have three processes, or three disintegrations that they undergo, which you have the negatron, the positron, and the electron capture. So the negatron, at the end of the day, beta minus is produced as a byproduct in addition to the daughter nuclide and energy. The positron, beta positive, is produced as one of the byproducts to the daughter nuclei and energy. And the electron capture, that one, the atom or the parent nuclei captures an electron, so that then they produce daughter nuclides. Okay, then we talk about gamma radiation. Now, a gamma radiation is not any atom. It doesn't produce any atom or anything of that sort, but then what it produces is just energy, and energy in the form of a photon. Energy is in the form of photon. So a gamma ray is a packet of electromagnetic energy or photon emitted by the nucleus of some radionuclides following radioactive decay. Gamma photons are the most energetic. Yes, they are the most energetic photons in the electromagnetic spectrum. The emission commonly occurs within a fraction of a second after radioactive decay, but sometimes occurs several hours later. The gamma ray is identical in nature to light or microwaves, but of very high energy. A key difference between gamma rays and X-rays is how they are produced. Gamma rays originate from the nucleus of the radionuclide after radioactive decay, whereas X-rays are produced when electrons strike a target. So gamma rays and X-rays are kind of similar, even though when you talk about energy, the gamma ray is very high energetic as compared to the X-rays. But then the main difference has to do about their production. So X-rays is as a result of someone can say photoelectric effects. So it happens when an atom, or yes, let me say an atom hits a metal surface, and then it ejects electrons and also energy. But then when I'm talking about gamma radiation, it's always gotten from a spontaneous emission of a radionuclide. Okay. Cosmic rays also include high energy photons, and these are also called gamma rays, whether or not they are originated from the nuclear decay or reaction. So cosmic rays also produce gamma rays, and cosmic, we don't really care whether it's about a radionuclide that is producing it or not, but always it's also a form of gamma radiations. Okay. Then we go on to some of the difference, properties between gamma rays and X rays. So gamma rays have very short wavelengths as compared to that of X rays, and we all know that energy and wavelength are inversely related. So if the wavelength is short, it means we have a high energy. But if the wavelength is long, it means the energy is very small. So gamma rays have a very short energy, telling us that they have more energy as compared to that of X rays. Also, they are more energetic than X rays and penetrate and are more penetrative than beta rays. But then X rays are less energetic as compared to that of gamma rays, and they are emitted from the nucleus. Yes, in the exception of that of cosmic rays. In the exception of cosmic rays, they are always emitted from the nucleus, where X rays are emitted by electrons. That's when the electrons is being ejected from the surface, then it's accompanied by X rays. Then go to gamma decay. The nucleus resulting from alpha or beta decay is very often in an excited state. So when we are talking about alpha or beta decay, it occurs when the atom is in excited state. That's when they are unstable, or when, let me put that, when they are unstable. Like an atom which passes from an excited state into the ground state, emitting a photon of visible or ultraviolet light or X radiation. An excited nucleus is also unstable and usually very quickly passes into the ground state. The excess of energy on its transition into the lower or the ground energy state carried away by the photon emitted by the nucleus. Of course, the photon's energy corresponds to the difference between the energy states of the nucleus and is of the order of magnitude of mega electron volts. This transition between excited states is called a gamma radiation. So when an atom is being excited and it's coming back to its ground state or its equilibrium position or its equilibrium level, the energy it releases is what we call the gamma rays. And the process of coming to that state is what's called the gamma decay. So a typical example is, or what I can use this to explain to us in our everyday activities, like assuming you have nothing, right? And all of a sudden someone dash you, let's say 100 cedis. Okay. So when you don't have anything, the way you are very quiet, the way you are so down, yes, the way you are so down, the way you are on my new business now is that is your equilibrium state, or you are in a state of yes, a state of equilibrium, because at that point immediately someone gives you money, it energizes your mind. You come to a state where you feel like, say, the higher boss, so you can do whatever you want. Okay, so that kind of money that you receive, it will put you to the excited state. Okay, now at the moment, I bet that is then you only gamma key. The process of this can be as in you are undergoing gamma decay. Now I'm kind of woody, and then now what they to say scam no the control aduane, right? Into the aduane now, and then what aduane now they that is what we call the gamma radiation. So the energy that is being released as you are coming down to your ground state now, that's the gamma rays. The energy that you are releasing is what we call the gamma rays. I hope I'm making sense.
Yes, sir.
Okay. So they normally have considerably higher energy than X-rays, which is why they are considerably more penetrating. They are likewise significantly more penetrating than alpha or beta particles. Gamma decay is relatively the mildest form of radioactive decay, since the nucleus merely cools, whereas its internal composition is unchanged. The energy released during the transition is by one of the following three interactions. That's the gamma ray emission, internal conversion, and internal pair reduction. Then go to gamma ray emission. Like the electron shell structure of the atom, the nucleus is also characterized by discrete energy levels. a transition between this level can be made by emission or absorption of electromagnetic energy of the correct energy. The energies of these photons from a few hundred kilo electron volt to few mega electron volt, characterizing the high binding energy of the nucleus. Energy level diagrams illustrate the specific energy structure of some typical gamma ray sources as shown here. So these are how some of the gamma radiations are being emitted. Okay, this is a typical way of which some of the gamma rays are being emitted. So we take cobalt now, it radiates to get nickel, and we realize in all cases, we realize the atomic mass is the same. That's for this to this. And why is it the same? Because we said when we talk about gamma radiation, the thing that's really have impact is the nucleus. Okay, the nucleus. So always the atomic mass is always the same. It's always the same. Just that the nucleus is what is undergoing this kind of spontaneous emission to release the energy and other stuff. So from the first state, at this point was the ground state, and they are excited to this state. Okay, so we are excited to this state. You know, it have an excitation of +5. Okay, so from here to here, it releases what? A negatron, right? So from the first state to this point, we get a negatron. So when we add a negatron to the 5, we get 6. So from this point to this point, then we get all that 6 being eliminated, then it comes back to the ground state. So from here to this point is where we get our gamma radiation. And that's the same thing that we have over here. From here to here, we have this energy as the beta, but then when it's moved from this point to this point, you have 0.66 mega electron volts of gamma radiation, which is being released as a form of coming back to its ground state. I hope it's clear.
So go over again.
You said?
Please go over again.
Okay. So with the first one, the cobalt, here we have +5, right? Now the first stage it undergo is what you call the negatron. Okay. So when it undergo negatron, at the end of the day, we are going to have SS6 electrons because you have 5 electrons here. So this one added to be 6. Okay. So it means this atom is being excited with 6 electrons. So we have to release these 6 electrons, then come back to the ground state. So in the process of losing these 6 electrons, that's where it produces the gamma radiation. So as the 6 electrons leaves the system, it comes back to the ground state. Okay, so the process of losing is that from this point to this point, this is the amount of energy that's being released, and that energy is what we call the gamma radiation. Is it clear?
Yes, sir.
Okay. So that's the same process they undergo. So this is a typical processes that produces some of the gamma radiations. Okay. They can go on to okay, let's go on. Most gamma sources are placed in the excited state as the result of beta disintegration. That's beta minus disintegration or negatron disintegration. Since electrons and positrons are more easily absorbed in matter, the beta particles in such source can be filtered out by enveloping them with sufficient absorbing material, leaving only the more penetrating gamma rays. Then go to nuclear isomerism. If 2 half-lives are observed in a given sample, is it necessary due to different isotopes? So we have this whole reaction and realize we are having the same thing, but rather we realize it's undergoing what? A negatron. Someone, any question?
please.
Oh, okay. So you realize this is undergoing a negatron reaction because this is the daughter nuclide and it's undergo this for us to guess what we have over here. Now, the PA was found to decay by emission of beta particles of two different half-lives of 1.18 minutes and the other of 6.66 hours. These two half-lives are due to two different energy states. So basically, you realize the parent atom, the half-life for that one is 1.18 minutes. But if you take the daughter nuclei, they say the half-life is 6.6 hours. So ideally, if you are talking about half-life, you realize if the half-life is 2 minutes, it should be 2 minutes throughout the entire process. But I realized there is a case where it's quite different because the daughter nuclei, which have a half-life of 1.18 minutes, now decay to a daughter nuclei, which the half-life of the daughter nuclei is not the same as the parent nuclei. And that was where the circular transient and the equilibrium or no case reaction was talking about. I'll get to the slides on that so that it becomes more easier to understand. Okay. The two half-lives are due to different energy states. Yes. That's the excited of the same nucleus. Such long-lived excited states of the same nucleus are referred to as isomeric states or nuclear isomers or metastable states and denoted by M next to the mass number of the formula. So if you see any mass number with M attached to it, you have to know that it's an metastable states that the atom is, and they are undergoing isomerism. That's nuclear isomerism. Okay, now what is the isomeric state? Most excited states in the nuclei make almost immediate transitions to a lower state, or some nuclear states may live very much longer. The ideal excitation is it's usually hindered by a large spin difference between levels, that's for forbidden transitions, resulting in lifetimes ranging from seconds to years. A nuclide which is trapped in one of these metastable states would thus show radioactive properties different from those in the normal states. Such nuclei are called isomers and are denoted by M next to the mass number in their formula. So yes, ideally, we know that if they are undergoing radioactive decay, they have to possess the same properties. But in some cases, never like that. You have the one which is undergoing a meta state and have one which is undergoing a normal state. And those two products are said to undergo nuclear isomers. Then we talk about annihilation radiation. The word annihilation is just an English word of which I think you all know what it means, right?
Yes, sir.
Okay. So another source of high energy photons is the annihilation of positions. The gamma spectrum from a thick position source will thus show a peak at 511 kilo electron volts, corresponding to detection of one of the annihilation photons, in addition to the physical characteristic of transitions in the daughter nucleus. Gamma ray spectrum of that sodium source, as observed with NAI. Detector position annihilation may take place in the detector or the source itself. So when I'm talking about the annihilation radiation, it's just a matter of the energy that is being produced is being collided with the parent atom, then for it to just vanish. That at the end of the day, we are not going to get any daughter and parent nuclei at that in that angle. Okay, then go to internal conversion. Gamma emission is the most common mode of nuclear de-excitation. Transitions may also occur through internal conversion. In this process, the nuclear excitation energy level is directly transferred to bonds such as electron gets knocked out of the atom. Atomic electron, rather than emitted as a photon, the electrons ejected in the process is known as internal conversion. And when they have kinetic energy equal to the excitation energy minus the atomic binding energy. And it's also called the internal conversion electrons. And they are also monoenergetic, unlike electrons from beta. I think this is just reading. I'll leave that one for you. Now let's look at the work example over here. Now we spoke of the annihilation. That's why we also have to talk about the internal pair production. So if the pair annihilation talks about both the parent and the daughter being dying off, then means pair production is where electron can also or an atom or a neutron can also divide itself into two. That's we have electron and also a positron pair. And if this electron positron pair come together, that's where you also have the pair annihilation over there. Now, don't stress yourself with this. Don't stress yourself. And we also spoke about the absorption distance when we are talking about the beta decay. That we said we gave this expressions where we said n is equal to n naught. N is equal to n naught times e my negative mu x. Where we said the mu is the absorption coefficient. The same way, if we want to find the intensity of gamma radiation at any distance, we can also find it. And this is how we find it. So the intensity at any distance, that's the energy at any point of the gamma radiation, can be found using this expression, where the I naught is the intensity of the source, and the x is the distance at any point, and the mu is the absorption coefficient. So at any point, you can find the energy or the intensity of the gamma radiation at any point. And mind you, the closer you are, the higher the intensity. The closer you are, the higher the intensity, because this equation even tells us that. Because assuming if s is equal to 0, if s is 0, everything here is equal to 0, and now the absorption intensity will be the same as the initial source, or the quantity or the intensity of the source at that point, which is very harmful. Because for gamma radiations, the further you are, the less intense it is, and the less harmful it is to you, even though it's harmful, but then the further you are, the more safer you are. And that's why sometimes in cases of radiation accident, they ask everyone to evacuate from that environment, because if you are closer to it, the higher you are to die early. But if you are away, the better you are to save your life. Okay. The absorption of gamma particles in absorbing medium is due to 3 types of interactions of the gamma particles. And the one is due to photoelectric effects, that's photoelectricity, and due to Compton scattering, and also due to electron-positron formation, that's pair production. So the absorption of gamma particles in an absorbing medium is due to just these 3 types, these 3 interactions, due to photoelectric effect, Compton effect, and also electron-positron formation, that's pair production. That's the above absorption coefficient has 3 components, where the mu p is the coefficient for the electric effect, the mu c is the coefficient for the Compton scattering, and the mu b is the coefficient for pair production. Okay. These different components are of varying significance for varying ranges of energy. For example, the mu b, that's the mu for the coefficient for the per production, doesn't exist for energy. It's less than 2 m naught e c squared. Where the m naught e talks about the mass of the energy at that point, or the rest mass at that point, um, uh, the atom which is undergoing that radiation, gamma radiation, the rest mass of that atom. Okay. As has been pointed out, above gamma decay is the type of decay that exists between isomeric states. So amongst all the three, that's the beta, alpha decay, beta decay, and the gamma decay. With the gamma decay is where we have it to exist in isometric states. And that also brings us to the end of this one. Then go to radioactive nuclide and radiocarbon dating, of which I know this one day. We always tell you to take the last part, but then this is also so easy for you to understand. So when you talk about, let me give you a brief overall brief distance so that we can close. We talk about radiocarbon. Radiocarbon is just a matter of already radiocarbon dating. It's a matter of tracing an artifact or trying to find how old a particle have lived, knowing its half-life. Okay, so some of the particles or nuclei that helps us in doing this kind of things is carbon, and that's where it comes. The name comes in radiocarbon, because carbon is the one that they be using in doing all this dating to find how long a particle or something has been in existence. That's all what this session talk about. On this note, I guess you can call it a day. Now the floor is open for questions and answers, if there is any.
Thank you very much.
You are welcome. Is there any question? Mr. Castro.
Sir.
Now only question be and now they also the able to only shake.
No question. I think what we did is just going through the motions of what we did for last semester. I'm okay with that, but said the can the
No, this course is not difficult. This one you'll be able to do is the one I'm just having more this one about is the EM field.
The electromagnetic field.
Yeah, by Shabua.
Allah, amen.
So on this note, Mr. George, and I'm Mr. George Wapon.
Mr. You see,
Mr. Ibrahim.
So don't worry.
Hello, sir.
Yes.
Hello, sir. Me and Francis.
Okay.
So this semester, they acquire last block idiot. Or some share. I saw their class will be done there. You.
What's the one short? Code for an answer.
Exam send your best set question because I say Adena which are near Ubechan wa wouldn't move near Uti and who into a tokra won't near offer. So near offer which also with you. Into my banner side, baby, I done
it is somehow like you really don't know how they sometimes mark the papers, because you look at something like you are doing a practical and theory aspect. You look at your practical, you get a high grade, but your theory you get a low grade. And sometimes to
Yes.
your theory you get a high grade, by your practical you get a low grade. But the thing is that the questions repeated themselves in the practical. So how is it that for one of them you get it high, for one of them you get it low? Sometimes the marking I really don't get it. Seriously.
It's sometimes not about the marking. With regards to that one, I think you see for the theory, the assessment is 40%, the exam is 60%. But for practical,
Yes.
assessment is 60%, the exam is 40%. So if you are being asked to go and do the reports and you do it well, you can even get a C without not writing the exam. Because if you do it well and you get 60 out of 60, that's a C. So exams, even if you get 10, you are getting a B. But then if
Ours
you
there
write,
is 40 still. It's still
no,
40 60.
practical is different. Practical is 60-40. Exam that is 40
Wow.
60. Yes. And with
Wow.
the theory, what I was not understanding is what you just made me aware right now. I thought maybe after writing your quiz, you get your quiz prepared to redo it again. Because some of the
There
No,
be
things
there.
are there, I'm
There be
thinking maybe you see the question, so you have to sit down and
there.
resolve it so that I don't repeat the same thing. But you just let me know that you don't treat you guys
Areho.
that.
You talk to
Areho.
them, but they are giving excuses that people will come later, come and write it because they were able to write it. But the thing is that you're doing work. You have to know where you got wrong, where you got right. Because even as a scientist, when you're doing an experiment, if you don't know your observations well, you always fail because you think that what you're doing is right because you don't know your outcome. But the thing is that what you're doing is always wrong. Do you get it? So I sometimes I really don't get it. I try my possible best to talk to all the management about it, but they keep repeating the same thing. I've talked to Dr. Valentina about it. I've talked to Dr. Lydia about it. I've talked to Professor Abu about it. I've talked to Professor Entries also about it. Like all of them, they're saying the same thing. They'll look at it, and later on, to someone will also say that someone won't be able to do it with a tangible excuse. So if they release it, it will be like a leak pass question. But I really don't get that logic that they are saying.
Wait, the exam, do you write it at your with your machine or you go to the center and you'll be using their machine?
No, we
You go
write
to
it
the
with our own machines. It's a website, so you just log into the website and you
No,
no
write
you
it.
go
can
into the
no.
center.
it,
He's talking about the exam. He's talking about the exam.
Exams, no,
Say
exams is
this, yeah.
paper. Exams is paper.
no, I'm talking about the quizzes.
The quiz
You go
is,
to
is
the center
online. That is, you use
online,
your
but you
own.
are restricted.
So you can be screenshotting your questions.
No, 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 no,
No,
no. You can't
restricted. Restriction.
because you're using your own device. Okay, so it is assumed that you can use AI. You can just go away from the website and use AI to solve the questions. So what they do is that they will shut down the phone with the app. The app will take over your phone. You will not be able to go to any place. Only the exams, the question pages that you'll be restricted to. So you can't go back. You can't go to the home button, anything. And you're supposed to use only one phone to do it. Do you get it? You're supposed to use only one phone to do it.
So so
Hmm.
So you can't screenshot anything.
so they call the app exam kiosk. And when you logged in into the exam kiosk, your phone is
Unlock.
locked
Your phone,
down,
You
your
unlock
phone
is
is
the phone.
hijacked.
deactivated.
Your,
So you
your,
can't do
You
your,
unlock
anything
your
apart
your
phone.
phone is
apart from that
hijacked.
interface.
But say you see you for that one, what has happened? Me, I want to ask about the thermal physics. Please, have you finished marking them?
Well, you submitted it to them long time before we even
Oh,
started
okay.
with the course.
So please, how was it? Was it okay?
Oh,
Did we do well?
you guys didn't do well, but then I don't say I'm sure they'll. I was just asked to mark, so I just marked gave it to them. But then I think they would because I think it was just one center. They were two. They were the only people who was able to get 40 something. The remaining it wasn't good.
40 something
Wait,
out of
40
60.
something out of 60.
Yes,
Hey.
I think 47 or so, and that was the highest.
Ah.
Yeah, but they will be dashing mass across board. So obviously it will be better. Because if they are to use the raw scores, it will be good. So
That's
definitely.
another.
Thermal physics. 40 something out of 6.
Yeah, we'll do something.
What? The thermal
Yeah,
was tough. Oh.
yeah, that was the highest.
The thermal was
Stop.
tough.
Oh, it's
I think that one the highest had objectives which I think say 16 out of the objectives. Some people were getting 7 and 6.
Hey.
So that was why I brought about that quiz questions because if you say Senkamumua, why would you do something? You wouldn't work on it.
yeah. What is it? This thing is worrying, though. It's worrying. Like it's really, really worrying. I don't know. I really don't know why they are doing that.
That's why you are a UCC student. You have to be tough.
Oh no. Sometimes some evolution is bad. You know, some evolution is bad. Sometimes some evolution is bad. Going blind, like in all aspects, we are learning. We are supposed to learn for future things. You get it? So if you are doing something and you're getting it wrong, at least you should know where you're getting it wrong, or else you're going to repeat the same thing. And insanity is repeating things over again, expecting different results. But this time, you don't know your results, so you think you're doing the right thing. It's bad. It's really, really bad. It's really, 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 really bad, especially for us. And most of the thing is that the same thing, just like we said, most lecturers will repeat the same objectives they did in the quiz and repeat it in the exams, expecting us to, if you got it wrong, expecting us to get it right. But here's the case, we don't even know where you got wrong. So we are going to choose the same thing again. And it causes this thing. And the thing is also that you won't be able to even remember the question because the questions are plenty. You won't even able to remember the questions for you to solve it later on.
Don't worry, Shabwa.
Yeah, and
Everything will be fine.
Sir Yusuf, the thermal physics. One question that came, we were supposed to write short notes on Maxwell's equations, but
Yes, I was not expecting you to write notes.
Yes,
Maxwell's equation was, I think, 4 pages. I just want you to just write them.
So we should write the equations.
That was all I needed. So
but you didn't tell us.
Notes on,
You didn't. You said we should write short notes. So we two were there.
I know.
How can you write short notes on Maxwell's equations?
It wasn't only about Maxwell's equation. I also asked you of Helmholtz equation, and I think
yes, it was a short note.
So I just want you to see.
They said write short notes. So we're there.
Short
like
notes means keywords. Pay attention. If you say short notes, be mindful of keywords. So the keywords is what you're interested in. So someone short note can be 2 lines. And the 2 lines will contain all those keywords. It's correct. Someone short note can be 1 page with no keyword, and the person will get 0. Oh, damn it! Students, well called GHM primary SHS University.
Right short note about Mr. Yusuf.
What's your questions? Notes bank. Did you see the man that was allocated to it?
Yeah, I don't remember, Mo. But was it like 2 or 3?
It was 6 months, 222.
Sometimes when you're answering questions, you have to also pay attention to the marks allocated because the mark allocated will tell you the quantum of thing you have to write.
2 marks. All the question, but all the equation, but only the 2 marks now.
Yes. That's what I did. If you write the Helmholtz equation, which is equal to H is equal to this one. F is equal to H minus EDS or something. I just give you 2 marks.
Right.
I don't need any.
Right.
Oh, but like we want to know so that the next one that will come on. Because especially when you ask it to derive, for instance, you ask it to derive the ideal gas equation. Frankly speaking, we are not expecting that. So and this to derive the ideal gas equation by stating Charles' law and Boyle's law.
People that one in China. Then why do we have to even worry about it? Let's think about
Oh,
what is left.
I'm asking
That's
because
very,
of
very important.
the electromagnetic field theory. You know, there are a lot of derivations of equations in it. Plenty.
Oh no. Abi,
And
I've told
since
you
you are the same
anything that's
person
not
handling
similar,
that.
I'll prompt you. Because the other day when
Oh,
we were
okay.
doing it, I think I told you to take note of one like that. So if I will need you to drive or something, I'll let you know. So don't worry yourself.
Okay. Okay, sir.
Right. Then we meet tomorrow, right?
There is
4 to 6.
metro.
Yeah, 4 to 6.
Say
Or it's 6 to 8.
it's 4 to 6. The
Yes.
Wednesday on that
What?
is 6 to 8. Is the Wednesday on that is 6 to 8.
Okay, sure, sure. Then we meet tomorrow, 4 to 6.
Mr. Ibi, Mr. Ibi.
Hey, EB. I don't know friend, so I will come with you all my friend. I day.
I am Professor Ompete.
I don't know how
Patrick
to
or
this.
Matthew.
I think you say have a wonderful day.
You're always welcome. Enjoy your Saturday.
Saturdays we can enjoy you. Now we don't enjoy our Saturdays, so our Saturdays and Sunday we can enjoy them again.
If
We are no longer enjoy our
if we enjoy our Saturday, unless 8th December, that
This time,
I'll be able to. If December, maybe I'll drink the Guinness like 7 bottles just to cover for all the for all the months I've lost.
enjoy, chill.